No.
You don't think you really care?
No. I can send those in the slides.
I guess if it's recorded,
She can watch the recording. Yeah.
Okay. I think it's a pretty good crowd when people are probably a few minutes. But let's give it 1 minute and we'll start.
I hope I talk.
I did.
How are you doing? Good. It's always good to check.
You can always just wing it with
Whatever slides are there.
Right. Yes.
I promised your grad students actually that I was going to put some funny pictures of us from grad school into the thing, but I ran out of time. Yeah.
Okay, good.
So I'll just show them later.
All right.
I'll email them the pictures.
Okay.
This is going to be recorded. Wait, it hasn't started recording yet. If I see anything,
Just cut it out.
Yeah, it did start at 3, so all the levels look good. All the content's everywhere. I showed so set to go.
Thank you very much for your help.
Yeah, and hold for a few minutes. If anything happens, I'll make sure you set.
Okay, thanks for coming, everyone. Today we are very fortunate to have Professor Johannes Pollanen join us. I will just give a very brief introduction for Johannes. He got his PhD from Northwestern University studying helium-3 superfluid, which is a very arcane field that very little people study that. It's very difficult, and he uses pulsed NMR to study how the stability of helium-3 superfluid phase interacts with the engineered disorder. And if I can quote his advisor, he literally killed the field. So after graduating from Northwestern, he went down to do a postdoc at Caltech with Jim Eisenstein. He studied various different forms of fractional quantum Hall effect using various different experimental methods, including transport and acoustic wave, a lot of very different experiments. And then he got a faculty position at the Michigan State University. He started a research group there and just decided that I'm going to do something completely different from any of his experience. Now he's studying how superconducting qubit work, as well as electron on the surface of helium-3 and helium, this helium liquid. And I should also mention that Johannes has ventured outside of the academic world. He has his own company doing quantum computation research. And that company, from what I know, is founded by venture capital, and they have a headquarters in Chicago. So for a lot of the inspiring young grad students, if you want to go into the field of quantum computation, we have an expert here as well. So without taking up too much time, it's great to have you, Johannes, and we are very eager and curious to learn what you can tell us.
Okay. Thanks. Thanks a lot, Leo. So Leo didn't mention, but he and I were grad students together for a long time and lived in the same sub-basement lab for a very, very long time, which was actually it was a wonderful set of collaborations that we did as PhD students. It's fun to be visiting again and seeing him and getting the chance to tell you about what we're doing in my group. So yeah, what I'm going to tell you today is, so Leo mentioned we do a whole bunch of different things in my research group, which is called the Laboratory for Hybrid Quantum Systems at Michigan State University. And today I'm just going to be telling you about some new results that we have on open quantum systems research using superconducting qubits and how we couple those to engineered phononic bads. Now, the kind of picture that I want you to have in mind in going into this talk is that, every quantum system that you want to utilize for, say, coherent manipulation, or you want to make into a qubit, you typically want to decouple it from its environmental degrees of freedom so that it can have really good coherence. You can do high fidelity gate operations. You can do all this kind of thing. But that's never really the case, right? I mean, every qubit is in some way coupled to its environment. And normally we think of the environment as being quite deleterious to the fragile quantum properties that we want to study or control. But it turns out that in certain contexts, if you can understand the environmental degrees of freedom and how they entangle with the qubit, the information that is lost to that environment, you can gain some information about that by playing with the quantum system in just the right way, and by engineering the bath degrees of freedom. And so I'll show you how we are doing that kind of thing in the context of phonons in the system. I'll mention also that MSU is part of a collaboration of universities that includes University of Michigan and Purdue. So if there are any undergrads in the audience or graduate students looking for postdocs, the Midwest Quantum Collaboratory, which we co-founded with those two universities, has a lot of opportunities for postdoc positions and graduate student positions in quantum information science. Okay, so I mentioned that the lab is called the Laboratory for Hybrid Quantum Systems, and I want to tell you a little bit about what I mean when I say hybrid quantum system. So typically what we do is we take some engineered quantum device or system that we have good control over, and we interface it with some other engineered quantum device that we have good control over at, let's say, the level of single excitations. And there's kind of two reasons that we like these hybrid systems. One of them is associated with just fundamental physics. We want to, nature ultimately speaks a quantum mechanical language, and we want to understand, how do phonons talk to qubits or electrons or photons. And in these systems, we can engineer interesting interactions between these quantum degrees of freedom, and to study how they talk to each other. And we can do this at the level of single or even collective excitations in these quantum systems. The other motivation for doing these kinds of experiments, I'm sure you've heard, is that if you can understand and control elementary quantum excitations with sufficient fidelity, then that opens the door to potential future quantum technologies for, say, quantum simulation or sensing, communication, or ultimately computation. And that's, I think, a compelling reason to try to do things both on the research side and on the technical side. Now, I'm only going to tell you one small part of what we're working on, what some of the folks in my group are working on, but I want to give you kind of a 10,000-foot overview first of all of the different kinds of things that are going on in my research group, just so you get a flavor for the kinds of systems that we work with and the kinds of things that we think are fun. And I'm happy to talk about any of these afterwards if you want. Just ask me. So as Leo mentioned, one of the systems that we study is hybrid systems that we can develop with this funny system of trapped electrons. It's where we place electrons above the surface of superfluid helium. So we create some device layer on a substrate, on a silicon substrate. It maybe has qubits on it, maybe has microchannels, and then we cover the whole thing with a layer of liquid helium-4, which forms a perfect dielectric insulating substrate. And we put electrons on the surface of that helium. They float there, and we can manipulate them with the device layer underneath. I won't be saying anything about but this platform is also the one Leo mentioned. I co-founded and helped run a quantum computing startup company based in Chicago. It's called AeroQ, and there we're trying to use the spins of these electrons to build a scalable quantum processor. But again, this is a story for another day. I won't be telling you about any of that, really. We have an ongoing research program to study other electron systems. These are ones that can be confined to 2 dimensions in, say, graphene devices or semiconductor heterostructures. And there, what we're really trying to do is to understand the many-body quantum mechanical degrees of electronic matter that can form at low temperatures or very high magnetic fields. In another part of our lives, we also work with hybrid systems in color center defects in diamonds. So you probably all have heard of the ND center, where you have a vacancy next to a nitrogen interstitial in diamond, and that thing can operate as a room temperature qubit with quite high coherence. And a part of the group is working on developing hybrid systems with these kinds of things. Again, I'm not going to have time to tell you about any of these, but what I am going to tell you about is the hybrid quantum systems that we're developing by coupling superconducting qubits to in particular, phononic excitations in piezoelectric crystals. So this is the main gist of the story, but I'm happy to talk about these other things later if you want. And if any of you are still on Instagram, my students tell me I have to put this up. So if you want to follow us on Twitter or Instagram, that's where we are. Or if you want to check out our website, that's hybridquantumlab.com. Okay, so that's kind of the 10,000-foot overview. But this is the story that I'm going to tell you about. So throughout remember, the name of the game is open quantum systems. We want to understand the dynamics, the steady state, the possibilities to engineer as a resource the dissipation of a quantum system, say a qubit, coupled to, in this case, a bath of phonons that we can engineer. So to tell you that story, I have to build it up in a few pieces. I'll have to tell you about our superconducting qubits, and then about this phononic system that we utilize, which is a surface acoustic wave device that we fabricate onto a piezoelectric crystal. So we're really using the surface phonons as the bath. That's the bath degree of freedom that we want to interface with. And then I'm going to put these together and tell you about how we can make hybrid quantum acoustic systems by putting these things into interaction with one another in a controlled way. And then tell you about what kinds of open quantum systems research we can do and interesting things that we've learned in that direction. I should mention one other thing. If at any point in time you have any questions, you don't have to wait till the end. You can just stop me, and I'm happy to take those questions at any point in time. Okay, so let's start with the superconducting qubits. So I don't know how much you all know about superconducting qubits, but please, ask away, or my apologies if it seems like I'm being pedantic. But so we want to make a two-level state out of a circuit that we can engineer and fabricate in a clean room. So what do? We want to make it, the quantum states that we ultimately want to control are quite fragile. So let's use a superconductor. That's a great, the superconductors are dissipationless. So let's make our circuit out of that. So the simplest circuit that you can imagine making is just an LC oscillator. Let's try that. Let's just put an inductor and a capacitor. Classically, the energy is stored between currents that flow through the inductor or charges that build up on the capacitor. And if we cool that system down, we can write down a quantized, Hamiltonian for the charge and flux degrees of freedom in this circuit. And in fact, it'll form a very well-defined quantum circuit with well-defined energy levels. The unfortunate thing is that each one of these energy levels is because this system is completely harmonic, this potential is parabolic, and these energy levels are equally spaced. So I can't isolate any two of them to operate as a qubit. If I try to send in a control signal with h bar omega, I just climb up this ladder. I can't pinpoint any two of those relative to the others. Just realizing, is there a clock in here? So I ramble sometimes. Leo, you're going to give me some kind of, you'll throw a coffee cup or something in here. Right? Great. Okay. So, that's unfortunately not a great choice for a qubit, and Schrodinger's cat does not like making qubits out of harmonic oscillators. So what's the simplest thing that we can do to kind of keep with this idea of making a circuit as a quantum object, but actually try to make a qubit? So thankfully, there is a solution. We can simply replace that inductor that was in this circuit with this little X, which represents a Josephson junction. And a Josephson junction is just this. It's just imagine, you have the superconductor, and I'm going to interrupt it with an insulating barrier and then another superconducting wire. And then the Cooper pairs in the superconductor can tunnel through this device. It looks kind of like a tiny little capacitor with a tunnel junction in it. And this thing functions as a nonlinear inductor, with the inductance varying as a function of the current that flows through it. So this thing is now, we've got this capacitor and nonlinear inductor. So let's see what that does. Here's actually a picture of what one of these junctions looks like. So here's a superconducting. This is all made out of aluminum. Here's a superconducting wire. The Josephson junction is buried under here, or the insulating barrier is under here, and then there's another superconducting wire on the other side. So this is great because I can, write down at low temperatures, I can write down a Hamiltonian. Actually, at any temperature, I can write down this Hamiltonian, but at low temperatures, I can realize this Hamiltonian for the charge and conjugate phase degrees of freedom across this junction. And the beautiful thing about this is because the inductor here, this Josephson junction, is nonlinear, the potential that traps excitations in this circuit is no longer parabolic. It actually has this cosine potential. And so that means that there's an anharmonicity to each one of these energy level spacings that's dictated essentially by that we can tune in fabrication. So we can just by designing the circuit in an appropriate way, we can make this anharmonicity more or less anything that we want. And now, because these are different by, a sufficiently large amount, we can apply a control signal to take the excitate, to introduce an excitation into the circuit, to take it from its ground state to its first excited state. And that excitation is distinct from the one that goes into the higher levels. So that's great. This is a good solution. And in fact, this kind of superconducting circuit where you have a Josephson junction that's capacitively shunted in this fashion is essentially it's called for the sake of introducing jargon, it's called often this kind of circuit is called a transmon qubit. And there's some history to why it's called that, but it sort of doesn't matter. But it forms the backbone of the superconducting circuit efforts at all of the major companies that are trying to use this kind of architecture for making large-scale processors for quantum computing. So, like, here's some qubit chips from IBM. This is an early one from Google. This is really early. This is actually still like, I think it might say UCSB on somewhere on the chip. And then this is one from Rigetti. So you can see these kinds of have like different flavors and looks, but this is all essentially at the heart of each and every one of these is a little, something that looks like this with a certain number of Josephson junctions, some capacitances. The geometries are essentially just capacitances. I'll mention there's one other important aspect. You see these like little meandering pads here. Those are microwave resonator circuits that are the qubit, like in this chip, the qubit lives right there, or right there, there. Those are the qubits, and these are control and readout resonators. So it'll become clear why one needs those control and readout resonators in just a little bit, but they're as the name implies, there for control and readout of the qubits. Okay, so we in my group use essentially a transmon qubit as well. We have a little qubit that has a chip on it. Chip that has a qubit on it, and we have a control and readout resonator as well. We embed this qubit directly into a microwave box that we just make in the machine shop. We mill out a slot into this box, and then we can send microwave signals into and out of these connectors, and that allows us to control and manipulate the qubit. And we can, do all the qubit experiment. So this is a single qubit in this microwave cavity, and we can do all the create superpositions, do readout, state preparation, tomography, all the things that we need. Now, if you zoom in on this chip, what you find in the center is one of these little Josephson junctions. Here's one of them. You see these wires that head down and up out of this zoomed in image. What they connect to is large millimeter scale antenna pads on this chip. So there's actually no wires that we connect to the circuit. We just embed this directly into the microwave environment of this box. And then these things function as a dipole antenna that allow us to free space couple the microwave excitations to the qubit. And I should add that here, the microwave cavity and the qubit frequencies we operate in are typically in the 5 to 10 gigahertz range. And that's really convenient because 5 gigahertz is in temperature units about 250 millikelvin. And so when we put this into the dilution refrigerator in our lab that cools down to 10 millikelvin, the device naturally cools into its ground state, as long as we do the filtering and stuff right. This thing just passively cools into the ground state of the circuit, and then we can do all the experiments that we want. Okay, so just a little bit more about exactly what I mean by controlling and reading out this qubit. What do we do exactly? So it's actually quite an interesting system in the sense that what we're doing is we're taking some quantized circuit, placing it in a microwave cavity. But when we're doing that, we're really just borrowing a page from quantum optics where, you take an atom and you place it into a cavity, a laser cavity. And here, the atom is the synthetic atom that is the circuit, and the optical cavity is the microwave cavity. And when you do those two things, what happens is the system is governed by something that looks like this Jaynes-Cummings Hamiltonian. So this is the Hamiltonian that describes the behavior of this composite system. So there's a term, a two-level term that describes the qubit. There's a harmonic oscillator degree of freedom that describes the cavity photons. So this is just the harmonic oscillator that is the microwave box. And then there's some coupling term. that describes, if you place a microwave photon into the cavity that's resonant with the qubit, you can promote the qubit to an excited state, or vice versa. Okay. And we often, go ahead.
So, so this qubit, I assume there's a loop.
Yes, this one doesn't have a loop. So you can have some that have loops, some that don't. This one here doesn't, but we often put a loop. We make a squid loop, so there'll be two junctions in a loop configuration so that we can put a magnetic flux through to tune the loop. This one just happens to be a single junction transmon.
So, what's not shown outside this red box?
Yeah, so it's just two large millimeter scale and rectangular pads.
And then up and down means what?
Oh, you mean what are the actual qubit states physically?
Yeah.
Great question. So this is actually the simplest. So this is a great question. So the qubit states actually correspond to the Josephson plasma resonances that develop over this junction. So you have a capacitor, you have the inductor associated with the junction itself. That you can think of as an LC oscillator, and charges will coherently tunnel back and forth. And there's in the language of Josephson junction physics, there's a Josephson plasmon that exists at 5 gigahertz, and that oscillation actually is the qubit state. But it's oscillations of charge across this junction. Now, if I have a loop, there's also currents. So the qubit state corresponds to tunneling of charge and the generation of currents around that loop.
So is the ground state and the excited state defined by different frequency of the oscillation, or?
No, just different. So the existence of the plasma oscillation or not, and then the phase is controlled by the phase of the charge oscillation across the pads. Did that answer your question? Now, I'll mention that we often operate this qubit in a regime where what we do is we can do perturbation theory on this Hamiltonian in the regime where we detune the qubit from the cavity. So we are going to operate the experiment in a regime where the qubit and the cavity are detuned from each other by this value delta. And if we make delta sufficiently large, this thing becomes a small parameter that you can do perturbation theory on. And then this Hamiltonian, this is like you can do this in your first year quantum mechanics class. You can regroup terms if you do perturbation theory, first order perturbation theory on this Hamiltonian, and you can regroup terms in such a way that you can look at the Hamiltonian as having a harmonic oscillator degree of freedom. This is a dagger A plus a half, that now has not the bare cavity frequency, but an additional shift that is imparted on it by the whatever the state of the qubit is. So depending on the state of the qubit, the cavity will experience a different shift in frequency. That'll be, keep it in mind for later. Yeah, go ahead.
So this is a single Josephson junction,
Yeah.
which is two antennas. But
Yeah.
we're still calling it an LC circuit. Is that?
Yeah, because the L is really the Josephson junction itself. So another way to think about it is there's a phase difference of the superconducting order parameter across that junction, and the L part is in the energy that's stored up in the gradient in the phase of the order parameter. So you have charge, that's the C, that's associated with the C, but the gradient in the phase of the order parameter as it goes across the junction has energy associated with it, and that's the L.
That's where the C comes from. So
It's geometry. It's just those pads, just by making those pads a different size.
So you're using the self-inductance of the wire.
No, it's the Josephson inductance of the junction. So it's really
Inductance is a magnetic field, right? So there has
So here the Josephson inductance is not really an inductance in the sense of a magnetic field. In some sense, it's an effective inductance that's associated with the gradient of the superconducting order parameter. Because the barrier interrupts it, and the phase of the order parameter has to be different on either side of the junction.
Yeah, so it's okay. This two state has to be associated with a quantization of something, right?
Yeah.
So it's either quantization of flux or charge.
In this case, it's charge. In the case of the single junction. Okay, so that's the superconducting qubit part. Now we want to couple that to a mechanical degree of freedom. And the mechanical degree of freedom that we're going to want to use is surface phonon on the surface of this piezoelectric crystal. And those things are called surface acoustic waves or SAW. And so what you should really have in mind is this surface wave that has a it looks like an ocean wave, but it's microscopic and it's on the surface of your favorite piezoelectric crystal, gallium arsenide, lithium niobate, zinc oxide, aluminum nitride, whatever you want. And what we're going to do is we're going to take one of these crystals, and to excite and detect these kinds of surface waves, what we're going to do is we're going to fabricate an acoustic Fabry-Perot onto the surface of the crystal. So imagine this is on the surface of the crystal. We fabricate some interdigitated transducer directly down onto the surface. That allows for if I put a voltage signal across this, a high frequency voltage, I'll launch surface waves to the left and right. And then what we do is we fabricate a series of metal strips on either side. They're really just metal strips. They form a distributed Fabry-Perot. So surface waves that'll go left and right will reflect off of these, and you'll form a cavity for the surface waves in this fashion. So you should really just have this kind of, with some effective link that exists in the cavity. And the neat thing is that these techniques, we can design devices like this and engineer their properties using a classical coupling of modes theory for these kinds of devices. And this is largely driven by the fact that these SAW devices exist inside of a lot of telecommunications devices. So they're in your cell phone, for example, as delay lines and bandpass filters. And so there's a whole machinery to do this classical simulation of how this device will behave. And so we do that to design it so that it'll have the right frequency and everything for our experiments. And just to give you a sense of the numbers, the speed of sound of these surface waves is about 4,000 meters per second on lithium niobate, which is our favorite piezoelectric at the moment. And so that means that if I fabricate a wavelength, which is just determined by the spacing of these finger gratings, I'll get a frequency of about 4 gigahertz, which is right in the range where we want to do our experiments. And I'll mention that, just like the qubit, 4 gigahertz is in a regime where if I just take this device and cool it in a dilution refrigerator, it will cool into the fundamental mode that's trapped in here will cool into its quantum mechanical ground state passively. Okay, so I want to say just a little bit more about how we actually design these devices. As I said, this central interdigitated region, this is just simulation. So this conductance essentially tells you, as a function of frequency, where the surface acoustic waves are launched. So they're launched over this kind of broad region. The mirrors we design and simulate to have a reflecting coating that has a reflection that has this kind of oscillatory pattern. That's just is produced by the periodicity of these metal strips. And there's some stop band over which surface waves are reflected quite highly, and then regions where they're not. And if you combine these two together, the coupling of modes theory allows you to just concatenate the independent microwave responses of these elements, and what you get is a device that looks like this. So this is what we tried to design in our device. So this thing traps a single mode that's well defined in the mirror stop band, but you can see that there's a series of surface wave states that leak out of the mirrors on either side. So you have this kind of broad continuum of states on either side. So this is what we wanted to design. And by changing fabrication parameters, you can make this mirror stop band really wide. You can host a series of modes with a well-defined free spectral range between the modes. But this is what we're going to be working with.
What's the GA in the y-axis?
Yeah, so this is an effective electrical conductance for these devices that comes out of this coupling of modes. The way you should really think about it is, in some sense, like, what is the amplitude response of, if I could try to drive the surface acoustic wave device with a variable frequency excitation, this is how the surface waves would be launched. The coupling of modes, because it's all in telecom, like the electrical engineers switch everything into effective electrical conductances for like the devices that they actually want to make.
What kind of Q factor do you get?
Great question. So with the devices that we're making now, it's about 7,000. Yeah, they're not particularly good. We're actually trying to increase that. People have made, those are easy to make. 7 to 10,000 is relatively straightforward to make. We'd like to get to the point where we can make Qs of 10 to the 5, 10 to the 6 for other experiments, and we're working on that now.
What kind of function generator do you use? What's the power output?
Yeah, so it's great. Single photon level, single microwave photon, but we're not using, you'll see, we don't actually connect a wire. This is schematic. We actually use the cavity and the qubit to mediate a coupling to this device. Okay, so now those are the two ingredients that we're going to put together. Qubits, SAW resonators, and why on earth would anyone want to do this? Okay, so again, there's a fundamental and an applied reason. So it's exciting to try to control mechanical degrees of freedom, in this case, the piezo phonons in this resonator at the quantum level. That would be fun. Can we actually manipulate, the phonons? Can we get them to talk to the qubit at the single phonon level? It would open the door to exploring new regimes of circuit quantum optics. Normally light is really big. So normally the qubits operate in light, being microwave light is big. We operate in the dipole approximation of the Jaynes-Cummings Hamiltonian. With this, we can get into regimes where the qubit is actually a giant atom, and the radiation, the phonons, are small in wavelength compared to the atom. And from the technical side, the speed of sound is, on these crystals is 5 orders of magnitude slower than light, which means that if you have a microwave photon at 5 gigahertz, it has some intrinsic length scale that's about like this. But if you could somehow, and so if you're Google and IBM and you're trying to build a quantum computer with this length scale in it, that's not terribly scalable. So you might want to slow down your excitation, and if you can do it with phonons, then you could squeeze that down by 5 orders of magnitude and have micron scale resonators and readout and control, which seems much more scalable. I already mentioned we can cool these systems to their ground state. And I'll mention we're not the only group doing this. This is some work from Andrew Cleland's group at the University of Chicago. This is from Per Delsing's group in Chalmers. And there's a bunch of other nice references here. A bunch of groups around the world are working on this kind of thing, using various phononic degrees of freedom to couple acoustics and superconducting qubits. Now, what we do is a little bit different in our architecture and in our design. So what we're going to do in our experiments is we're going to fabricate one of these acoustic Fabry-Perots onto a chip. We're going to put some spacers on the chip, and then we're just going to flip a qubit directly on top, and we're going to use these large-scale antenna pads, the ones that exist on the SAW resonator and the ones that exist on the qubit, to mediate a capacitive coupling between these two chips. They don't touch each other. They just talk to each other via these parallel plates. And then we're going to take this whole thing and embed it into one of these 3D cavities. And then the name of the game is to try to engineer some interesting Hamiltonians that have both microwave photon excitations, qubit excitations, and phononic excitations, and see what we see. Okay, so that's what we tried to do. This is what the actual devices look like. Here's one of these surface acoustic wave resonators that we fabricated. It has these big antenna pads on either side. Again, that's mainly to mediate the coupling to the qubit. So when we place them on top of each other, there's this parallel plate. Here's the SAW resonator. Here's the interdigitated, fingers in the middle, and then the mirrors on either side. Here's the flip chip stack in a 3D cavity. So this device here actually has a qubit that has a squid loop in it. So there are 2 junctions in parallel with one another, so that we can apply a magnetic field to this and tune the qubit frequency with that magnetic field. And then the name of the game is let's see what kind of fun experiments we can do now that we've got this thing working, or at least built. Oh, I'll mention one other thing, which is, so the superconducting qubits coupled to microwave resonators often gets referred to as being studied in the framework of circuit quantum electrodynamics, CQED. This field of quantum acoustics already has its own horrible acronym, circuit quantum acoustodynamics, but it's essentially the same idea. We have a bosonic mode, the phonons, and we're going to couple it to the qubit in a Jaynes-Cummings kind of fashion. Okay, so here's what the first data for this system looks like. So here I'm showing you that simulation of the SAW, what we designed this SAW device to have. It has this confined mode, and then these continuum states on either side. And what I'm measuring here is the qubit spectroscopy. So we're measuring we're essentially sweeping the transmon frequency using that magnetic flux and looking at where the qubit excitations live. So down here, this line corresponds to the qubit as we apply a tone to the microwave cavity. And as you can see, as we get close to this place where we have this confined saw mode in the resonator, we see an avoided crossing, indicating that we can coherently couple to the qubit. I mean, can coherently couple the phonons in the resonator to the qubit. And in fact, in this regime right here, because of this avoided crossing and because of the parameters that we measure here, G is the coupling between the phonons and the qubit. Gamma and kappa are associated with the loss of the qubit and the loss of the saw resonator. And in this regime, when you get into this avoided level crossing, we're in a regime where the coupling between the two elements is bigger than either of their losses, and we can essentially coherently exchange excitations between the qubit and the saw resonator. In this case, it's at about a frequency of 10 to 15 megahertz. And so this kind of coherent quantum acoustics has been studied by us and by a number of other groups, and is a hallmark of the ability to hybridize these two kinds of states. But one of the things that you'll also notice in this data that's interesting are these fringes and where the qubit state sort of disappears and then comes back and disappears and comes back. And what's going on there is that we're in a regime where we're coupling to these continuum states, and the coupling between those modes and the qubit is much weaker than the loss of, or comparable to the loss of the cavity and the resonator. Go ahead.
What is it that you're measuring there?
With the
to evidence the qubits or not?
Oh, you mean what tells us that we're in this regime?
No, not even that.
Yeah.
Just like the measurement that you use in order to get that
this red line say. Yeah, that's right. So what we do is we have the qubit and the cavity in this. We have the flip chip device in the microwave cavity, and we're actually just measuring the transmission through the microwave cavity itself. That's actually all we ever measure is the microwave cavity that houses this whole thing. And then depending, if we cool down to low temperatures, that cavity and whatever device we have inside of it will hybridize based on that dispersive coupling thing that I showed you in the earlier regime. So depending on the state of the device, the cavity frequency will shift or not. And we infer that by sitting at fixed frequency and monitoring the cavity transmission. So we just send a fixed frequency tone into the cavity. And,
Thank you.
Yeah.
I'm wondering, you're coupling a lattice vibration
Yep.
to the
A surface wave, yeah.
a surface wave. So the Josephson junction, that current is exponentially dependent on the distance. Right?
Yes.
So it could be that you are actually essentially just expanding that gap up and down a little bit, and that was rather than the capacitive coupling. Rather, it could be just directly coupled to the thickness.
Yeah, well, so I should mention one thing. These chips are quite far apart from each other. They're about 40 microns apart, so they're really far apart.
But still, you have acoustic waves, right?
Yeah, but the wavelength of the acoustic, the amplitude of these acoustic waves is angstrom scale. And these things are 40 microns apart. And so what we've engineered we actually engineer the coupling to be a certain value based on simulations. And we do it via this capacity.
I'm assuming you use aluminum oxide as the junction.
Yes, on the chip, that's right. It's aluminum oxide.
That's like 10 angstroms. So if you have 1 angstrom displacement there, that's...
Right, but that 1 angstrom displacement is 40 microns. It's miles away. So these are on 2 separate chips that are...
I'm just wondering.
Yeah, they're, and the other thing is that we can control the coupling by just changing the size of those pads. So that may be a simpler way to say that you make the pads bigger, you get bigger coupling. So it's the pads.
So you can treat the tunneling property as a constant.
Yes, it certainly seems that way.
Is there some way of picturing the microscopic interaction of the phonons and whatever is on the squid itself?
Yeah, so it's really, we really just are, go back. Like you should think about these chips as being just separated from one another. And so if you develop a voltage difference here, it will capacitively couple to it's through these antenna pads. We're just making parallel plates. I think it's really just the electrodynamic voltage charges that build up on the plates that drive they take a qubit excitation and turn it into a phonon or vice versa. Okay, so we want to be in this regime where we study this. And actually these kinds of fringes correspond to what's known in circuit quantum electrodynamics as the bad cavity limit of that kind of effect, where what happens essentially is the loss, you put an excitation into the phonon system and it disappears before it can come back to the qubit. And so the qubit just forms a series of dark states. So that's the first indication that we have some dissipation that's important in this system. And so remember, now what we want to, so that kind of just shows that our device works. And what we actually want to do is something a little more sophisticated than just show, that we can coherently couple soft phonons and qubit excitations, or that we can, if we lose a soft phonon, we can kill the qubit. Like, that's less interesting. So what we're going to do is we're going to try to do this open quantum systems research. But to do that, we need to, in addition to dissipation, what we have to do is we have to introduce a drive term. So we actually have to manipulate the qubit dynamically in order to see how it responds in the combined presence of the drive and the dissipation. So don't worry about this. Is just a highlight. Drive is an important part. I'll get into the details in a minute. And then what we're going to do is we're going to model the whole thing in terms of a Markovian master equation for the density matrix of the qubit. So it'll have some coherent part, and then it'll have some dissipative part in terms of that Lindblad dynamics. And yeah, then we're going to see if our experiments match what this kind of theory predicts or simulates. And I'll mention this kind of bath engineering that's been done in these superconducting qubit systems has been done for some time by a variety of groups, but they've all done it in a photonic system. So they've used microwave photons to do bath engineering experiments. We're trying to, I think, there's nothing more ubiquitous or nothing more quintessential of a bath than phonons in some sense. Phonons are like the best environmental degree of freedom in my mind. Okay, so first step in trying to think about this physics, we need the qubit coupled to its environment. So just qubit dissipation. How am I doing on time? Oh, it's right there. Great. Like I said, we're going to use this Markovian master equation where we have the density matrix. And so the density matrix just encodes, the qubit and whatever environmental degrees of freedom that we have that we don't know about. And here the dissipation in the system is going to be described by these various operators that drive transitions in the qubit. So sigma minus, sigma plus, and sigma z. Now, just to give you a sense, and to connect with the experiments that I'm going to show, the way we're going to compare to this theory is we're going to perform state tomography of the qubit. So you can think of the qubit state as living as a vector on this Bloch sphere. So if I have, for example, the qubit in its ground state, I'll have a pure state that lives right on the surface of the Bloch sphere, and that's great. But I can have other things. So for example, if the qubit loses some information to its environment, it will no longer live on the surface of this Bloch sphere. It'll live somewhere in the middle. And the density matrix, by measuring the various tomographic components of this vector, we can reconstruct both the dynamics and the steady state of the total density matrix. Or, if you lose all the information, your qubit eventually lives at the center of the Bloch sphere and it's completely uninteresting. And we're going to parameterize the amount of information that we can extract from these kinds of measurements or this kind of theory in terms of the state purity, which is related to the trace of the density matrix squared. So, right, the density matrix has to be trace 1. We're always going to find the qubit when we do a measurement. We always find the qubit in ground state or excited state. But if we take the trace of the density matrix squared, then we can get some information about how it's interacting with the environment. Okay, so we also have to understand the dissipation. If we want to do dissipation engineering, we better understand that dissipation. So what I'm showing you here is our experiment to show that we can do that. So here, I'm plotting the relaxation rate of the qubit. So this is essentially 1 over T1 of the qubit as a function of frequency. So we're really far away from that avoided crossing, that single mode. We're in the regime where the phonon, we're in this continuum of phonon states that leak out of the mirror. And the blue data are the measurements of T1, and you can see it follows this form. The red is an analytical fit to the functional form of the SAW transducer conductance. So that matches pretty well. The green is not a fit. It's just what we simulated when we made the design parameters for the device. And if you modify our design parameters by about 1%, that corresponds to the difference between the data and the green curve. So, okay, cool. We can dominate this qubit loss via surface phonons. And we can have quite a variety of values for that. So keep this picture in mind. We can control T1 by just emitting into SAW phonons. Okay, so we got dissipation. Now we need drive. Remember, I told you we have to drive the system a little bit to actually look at the interesting dynamics. So what we're going to do is we're going to apply a microwave drive that can Rabi drive the qubit with some frequency omega, and it's some detuning from the qubit frequency delta. And if you apply a qubit, if you take a qubit and you apply that drive to it, the Hamiltonian will look like this. But this is not diagonal in the qubits in the computational basis of the qubit. And so in particular, you can think about this driven system in terms of a rotated frame on the Bloch sphere, where this angle theta essentially tells you about how hard you're driving it and with what detuning. And then you can really think about all of the states of the qubit, the ground state, the excited state, as being rotated in this driven frame. So you get these tildes. Or you can think about the operators as being rotated in the driven system, so by that angle. So for example, sigma z becomes sigma z tilde in the driven basis, and this is how you relate the driven basis to the basis in the lab frame. And if you do this rotation, you then get a diagonal Hamiltonian in the driven frame, but now you have qubit states, or effectively new qubit states, that are split by the generalized Rabi frequency, which essentially encodes the drive parameters of the qubit. Okay, everybody happy with that? Now you have to rotate the entire Markovian master equation in the same way, because we want to include drive and dissipation and model it in this Markovian way. And take my word for it, this is what you get. So there's a part that's coherent, that deals with the coherent dynamics of the system, and then all the stuff in blue is the dissipative part. So we're driving it in the presence of well-defined dissipation that we understand. Now, you'll notice that there are these two rates, gamma plus minus. They're the ones that drive transitions between this G tilde and this E tilde state in the driven basis. And if there's normally if gamma plus equals gamma minus, you're just going to get equal amounts of G tilde and E tilde. But if you can control the dissipation, then you can be in a regime where one of these is bigger than the other, and you can actually preferentially stabilize dynamically one of these two states. And this is an overall decay rate that you have to include. Okay. So what we're going to do is we're now going to actually do the experiment. So that's the theory we want to test, we want to play with. So we're going to park ourselves at some fixed qubit frequency, say right here near 4 gigahertz, where the qubit loss is actually varying quite strongly as a function of frequency, and we're going to apply the drive to the qubit, and with these drive parameters. And then what we're going to do is we're going to drive the qubit for some amount of time, and then we're going to perform state tomography. So we're going to drive, and then we're going to measure the expectation values, sigma x, sigma y, sigma z. And then we're going to repeat until we have a lot of statistics. And then we're going to do that as a function of how long we drive the qubit for. And so that the blue, green, and red data points are the state tomography that we infer after we perform this drive and the measurement. And then if the qubit was just decaying, and if the qubit was just decaying to nothing, all of these would go to 0. But as you see, they go to some. This one, sigma y goes to 0, but sigma x and sigma z go to some finite value. which means that we're not decaying back to the center of the Bloch sphere. We're actually decaying to some stable point for drive durations that are quite long. I'll mention the natural lifetime of this qubit is about 100 nanoseconds. So here we're driving it for, an order of magnitude longer, and we're dynamically stabilizing to a particular point on the Bloch sphere. And if we take these things, we can actually calculate the state purity, which is related to the density matrix, the trace of the density matrix squared. And what we find is that we can stabilize a state that has a purity of about 85%. And that's just for these drive parameters, it happens to be one particular point in the Bloch sphere. Okay, so we're not decaying, notably, we're not decaying to the center. So we're not going to this position here. Now, another way to think about this dynamical stabilization is in terms of the fact that you're driving the qubit, these new rotated quasi-energy states, E tilde and G tilde, they're separated by something that's of order the Rabi frequency, which is like 10 megahertz. And you can, when we're out here at very long drive, the system is actually in a steady state. We're driving it and it's dissipating into the phonon bath, but it's in a steady state. So we can define an effective temperature. We can, the average energy of that state is essentially just given by this, right? The expectation value of this sigma z operator in the rotated frame. We can apply some statistical mechanics. We can write down the partition function for this system and calculate, we can relate the effective temperature to this sigma z value. And we find that in this region, if you do this, the qubit is actually, if you were to, the effective temperature that you would associate with this stabilized state is about 250 microkelvin, far colder than the 10 millikelvin that the dilution refrigerator is hanging out at. Now, this isn't, nothing is really in some sense at this temperature, right? We're saying that if you had a qubit that had a temperature, if you had a qubit that had an energy spacing of this 10 megahertz, if you wanted to get the kind of stabilization that we're achieving, you would have to cool it to about 250 microkelvin in temperature. So to give you a point, Leo and I used to do adiabatic nuclear demagnetization experiments with helium-3, and we never got to any kind of, we would get down below a millikelvin, but not to these kinds of temperatures. So we can actually we can map out this whole diagram. Oh, I should have said, I totally missed. So the dotted lines are the simulation based on the master equation with essentially one fit parameter. So we can get both the dynamics and the steady state in the context of that Markovian master equation. And we can do that at a whole bunch of different points. So we can do it right here, for example, where the loss is kind of flat. And what I'm showing you here is various drive parameters. So this is Rabi detuning. This one is the Rabi frequency. And the color map here is sigma x. If we do the experiment there, we can get state stabilization. And we're again doing, the color map is just the tomography of sigma x. We can do it over here. You'll notice there's this region that's white. That's referred to colloquially as the band of zero coherence. This is where those jump operators sigma plus and gamma plus and gamma minus actually balance each other, and you don't get any stabilization, dynamical stabilization. Or if you go over here, where we did it before, sigma x careens downward. This is all great, looks beautiful, but we can compare with the Markovian master equation simulation. So this is again with essentially one fit parameter, and you can see great correspondence between what this driven dissipative theory works. It works for the data. These are just line cuts. And this gives you a sense of, what values of sigma x and sigma z we can stabilize in this framework. We can essentially get all of sigma x. We only really get the top half of sigma z. And we think we understand that in terms of we have a lot of global dephasing in the qubit. And it's a device thing that ours is not particularly good, but we could, in principle, improve that. But that's in some sense neither here nor there. Now, we've written this up, it's in review right now. Hopefully it'll get accepted soon. But I hope what I've shown you is, we've developed this phononic open quantum system where you can understand the coupling of a dissipative phonon bath to a driven qubit system. We can use it to prepare and dynamically stabilize qubit states, which is fun. In looking forward, kind of what we want to do is to think about how in the presence of loss or gain, for that matter, you can engineer effective non-Hermitian Hamiltonians with these qubits. So that's really fun because normally, you learn in quantum mechanics that Hamiltonians are Hermitian. They have real eigenvalues. They have orthogonal eigenvectors. That's a subclass of things you can do in quantum mechanics. You can have non-Hermitian Hamiltonians that have, eigenvectors that coalesce onto one another, and you can actually find interesting topological exceptional points in the eigenvalue spectrum of those Hamiltonians. So that's something we're actively working to do next. I'll just say real quick one thing. So that was the bath engineering thing. It turns out we can also use the qubit kind of as a sensor more broadly for the phonon environment. So if we park the qubit way over here somewhere where it's not interacting with the phonons, and we send in a separate microwave tone that can populate the SAW resonator, it turns out we can free space couple to the SAW device also. So we just put microwave signals in, and we can put phonons into the resonator, independent of the qubit. In that case, the qubit frequency, we're doing just perturbation theory on the Jaynes-Cummings Hamiltonian again. The qubit frequency will then pick up a shift that depends on the population of phonons in the resonator or in the device at all. And you can think of this as this is an AC start shift, essentially, due to the piezo phonons. You can do it with whatever, as long as you have a bosonic degree of freedom, that thing can start shift the qubit if you can get interaction. So there's a start shift in this dispersive regime. I'll note there's also a Lamb shift that we can't measure. It's too small. We don't know how to vary it. And if we do that, if we measure the shift of the frequency, shift of the qubit as a function of this AC start power that we send in at this separate frequency, we see a shift of the qubit, and we can, populate the qubit with relatively few phonons. We get a frequency shift that's about 1.5 megahertz for every phonon that we put on average into the device. And I'll just put a little advertisement for a new paper that we just put up on the archive. It turns out that we can actually interrogate the interference of the phonon modes in this device down at the level of several phonons using the qubit in this fashion. So if you're interested, ask me afterwards, or you can look at this archive preprint. Okay, so with that, that's the end of the story. I get to tell people about all this work, but these are the folks who actually do the heavy lifting on these experiments. The stuff that I told you mainly about today was started by former grad student Justin Lane, but is really being spearheaded by Joe Kitzman and Cameron Undershoot in collaboration with all these folks. Camille Michaelis and Austin Schleusner really push forward on the electron on helium effort. But yeah, it's a very collaborative, and these folks are terrific. And finally, I'll just thank, none of this would be possible without my colleagues at MSU. All of the qubit work was really started with a collaboration with my colleague Gator Murch at Washington University St. Louis, and of course the folks who fund this. This work in particular was funded by the National Science, mainly by the National Science Foundation, out of the Electronics, Cyber Systems, and Electronics, Communications, and Cyber Systems Division. And with that, I'll take any questions that you have.
I have a general question.
Yeah.
What are the advantages and disadvantages and challenges of the superconducting qubits versus the electron on the surface of helium?
Yeah. Superconducting qubits are, each one is a little unique. They're all a little bit different. The fabrication isn't sufficiently well defined. IBM is working to make it better. Each time they make a qubit, it's a little bit different. So that's problematic. You don't have. It's okay if you need to tune up, 10 qubits. It's okay if you need to individually by hand tune up 100 qubits. If you need to get to 1 million, it starts getting pretty painful. So the electrons are identical, which is nice. And we know that the control hardware that we can build into CMOS can be quite heterogeneous. The superconducting qubits also have this one intrinsic problem, at least when you're thinking about from the scaling perspective. You build in a pretty large length scale with a 5 gigahertz microwave frequency photon. So you have microwave resonators that have an intrinsic length scale in them that is like this. And there are ways that you can multiplex so that you don't need as many resonators for qubit, but there's a big length scale built into the superconducting qubit. The phonons are actually a nice idea. Amazon is pushing hard. Their internal quantum computing effort is pushing hard on phononic control of qubits, superconducting qubits. There's ways to maybe squeeze that down using high kinetic inductance materials, so you can get mode volumes that are smaller. But yeah, I would say size and heterogeneity are the most make electrons more exciting than superconducting qubits.
Thank you. Nice, very nice talk.
So the department does have another talk that's going to happen right now, but this is a very exciting talk. So for those of you who wants to ask more questions, let's come and afterwards. Okay, so that for those who need to go to the other talk, you can do that.
Thanks for listening.
Nice meeting. Yeah, I'll go to the next.
Yeah, good luck with your
Okay.
Sorry, very cool. I just wanted, like, so I think you commented on this in the end, like, so how realistic do you think it is, like, to use the specific superconducting that you're talking about as a control for the phononic control? Like, in terms of the footprint, though, you said it's like kind of sort of close to like the qubit footprint itself.
Yeah.
But, like, do you think that's a viable way to?
I think so. We're not pursuing that, but certainly the Amazon folks think this is very viable. Actually, what they're trying to do is they're trying to use the phononic modes themselves as the qubits. Mm-hmm. So, like, do you know this Rob Sholkoff's group and now his company uses the 3D microwave cavity modes as the qubit with the nonlinearity introduced by the physical qubit, but the actual qubit is the cat state of the photons in the cavity. Mm-hmm. So Amazon is actually trying to make phononic cat states and to build a much tighter packed, scalable processor that way. Mm-hmm. I think it's actually, I think there's a lot of,
said maybe 160.
Now, one of the tricks is, as soon as you have these
166 or 168. I don't know. They couldn't have this room.
Actually, something that
this room
highlights
cuts off at 4:30.
When you apply microwave signals,
The engineering.
we
normally had, so they kicked us out of seminars in here now. Just this week and next week, and
so actually in
2 weeks from now we get it
we
back.
have these big antenna pads.
Mm-hmm.
Yeah, so next week it's going to be early time slot again.
Saw modes. But what you would always see is these weird notches in the cavity transmission. Mm-hmm. They're all 7 megahertz split from each other. Like, what the fuck is this? They're always there. We thought it was a broken cable for a long time. Then we realized, like, if we took the qubit and we rotated it by 90 degrees, they were gone. And what it turns out is it's bulk phonons that were, because of these big antenna pads, we actually launch a bulk phonon to. And we can couple that to the qubit as well.
Okay.
And so I think one of the big challenges is going to be in device design so that you eliminate coupling to parasitic phononic loss channels.
And that's mostly related to geometry. It's not really the material. You said like lithium iodide is your preferred material.
Right now, lithium iodide is actually kind of junky. It's maybe not the best choice. You can make higher quality factor devices in quartz and in Conrad Leonard's group at NIST is really pushing on quartz devices and trying to understand. So you're right. It's geometry and it's like crystal cut, like there's these beam steering effects and diffraction that can happen out of the mirrors, but it is ultimately like it seems like an engineering problem to figure out. They're much more.
I gotta run in.
Yeah.
I just wanted to say great talk.
Oh, that's great. Yeah, hopefully, yeah. That's good.
Okay, thank you. Yeah, probably.
Sorry,
also,
I don't want to interrupt you guys.
no,
I just wanted to,
But yeah, Cleland's group has shown that you can control qubits with the phonons. You can actually take an index. You can entangle two qubits in a phononic channel. They've done a lot of really nice work in that direction. I think it's not crazy.
No, it's not crazy. I mean, I was like, I haven't like followed the field like specifically in this field, but yeah, it's it makes sense. Like I was at some point only thinking like you take this qubit and you want to entangle to link it to the environment, but at the same time you engineer the environment so hard that basically you sort of like couple it to a specific mode.
Yeah.
Is that then still like really like considered like environment? I mean, it's like what?
No, it's right. In some sense, it's not. I mean, it's like in some sense, we're just gaining better control. I mean, one of the things I think is fun about this stuff is like, I started as a condensed matter physicist, right? And you're always like, you're given whatever system you have, and then you try to like look at it different ways to understand.
Totally.
But here we're like, can we make it into this, and then see if it couples the way we think it should from
from the book,
like just a Hamilton, we write first year quantum mechanics.
I like that very much.
Yeah, it's awesome. It's another way to say it is like, it's all just a trick so that I can do more quantum mechanics. I think quantum mechanics is cool. And
Off the records.
yeah, hopefully it's not still recording. Cut that part out of the recording.
Okay, cool.
But
Yeah, thanks a lot. I probably also have to the other talk.
Okay, awesome.
Perfect.
Yeah.
All the best.
I forgot to send an email. It was supposed to be this Monday.